Our comparison of capacitors and inductors is now going to lead us to defining electromagnetic energy density. So here's our parallel plate capacitor with a top plate of area A and a separation D between the plates. Here's our solenoid with cross-sectional area A and a length or height H. And we've got our expressions for the capacitance and for the inductance. And from Gauss's law and Ampere's law, we can get expressions for the field strength inside each device as a function of charge on the plates in the capacitor case, and as a function of current running through the wire in the solenoid case. So we're going to consider the ideal capacitor and the ideal solenoid, where the E field inside is uniform and equal to this value everywhere inside, and 0 on the outside. And we'll neglect any fringing that occurs near the edges. So a nice uniform non-zero E inside, 0 outside. Likewise here, we'll have a nice uniform non-zero B inside, given by this value, and then a 0 magnetic field outside. And again, we'll ignore the fringing that occurs near the edges here. So these are our ideal devices. Let's write down again the expressions for the energy stored in each of these devices. So in our capacitor, 1/2 times 1 over the capacitance times the total charge on our positively charged plate squared. And here 1/2 Li squared, the inductance times the current running through our coil squared. So with each of these expressions, I'm going to make some substitutions. I'm going to replace capacitance with this. And here I'm going to replace inductance with this expression. And then I'm going to replace the charge Q with epsilon naught times A times the field strength. And here I'm going to replace the current I with the field strength divided by mu naught n, little n, the turn density. So what I'm trying to do here is get the energy stored in each device in terms of the field strength in each device. Okay, so here are those substitutions. And we see the number of cancellations occur, and it simplifies down to this for the capacitor and this for the inductor. We see that the energy stored in each device is proportional to the strength of the field squared in each device. The E field here for the capacitor and the B field here for our solenoid. Out front, we've got our constants, epsilon naught over 2, in this case 1 over mu naught, and the factor of 2 there. But then in parentheses, I've got this combination. The cross-sectional area, or the area of this plate, times the separation, D, and here the cross-sectional area of our cylinder times that height, H. You'll notice that these two expressions in parentheses are volumes. A times D would be the volume of the rectangular box enclosed by those two plates. This A times that D is the volume of the box. In fact, the exact volume of space where we have a non-zero electric field. For our ideal capacitor, there is this field strength everywhere throughout this volume right here, and E is 0 outside of that volume. Likewise, A times H here, that's the exact volume of our cylinder. So that's the volume of space where the B field is non-zero, and B field is 0 everywhere outside of that volume. So given that these two expressions involve field squared and a volume, this invites us now to define the energy density in each case. If this is the total energy stored throughout this volume, then we can take that energy and divide by the volume to figure out the energy stored per unit volume in any given small cube of space inside here. Likewise, if this is the total energy stored throughout this whole volume, then we can take that energy divided by the volume and get an expression for the energy per unit volume stored inside any particular little subvolume inside our solenoid. I said divide, but really we'd be taking a derivative here. So I'm now defining two new things. This is a lowercase u here, u sub e, for the electric energy density, or the energy density in the electric field. That is the derivative of this with respect to the volume here. Since capital V is potential, I'm just going to write VOL for volume, so we're not confusing that V with V for potential. So DUC, d volume, this represents the energy per unit volume stored in the space between the plates here. And it turns out that that is this simple expression, epsilon naught over 2 times the field strength squared. What we're seeing here is that the field itself is storing the energy. If there's field at a particular point in space, then there is a certain density of energy being stored in that space. Over on this side, this is a little u sub b for the energy density being stored in the magnetic field. So I'm taking the derivative of this expression with respect to volume here, du, d volume, this volume, leaving us with just this simple expression, 1 over 2 mu naught times the magnitude of the B field squared. This is the energy density in the space inside our solenoid here. Energy density, that's joules per cubic meter in SI units. So we're addressing a question here that may have occurred to you in the past whenever we've talked about the potential energy of a system. Potential energy is always a little bit more hard to grasp than kinetic energy, I think. When you say an object has kinetic energy, you know that that moving object is carrying that kinetic energy with it. But when you say a system has potential energy, you might wonder, well, where exactly is that potential energy? This U that the capacitor is storing, where is that energy? Where is it to be found? Could you locate it? Could you point to a location in space where that energy is? And this U that our inductor is storing, where is that energy? Could you point to a location in space where that energy is being stored? We now have an answer. The answer is yes. You can point to where the energy is being stored. You can point out where the potential energy is. It is being stored in space itself by the electric field. And here, the energy in our solenoid is being stored in space itself by our magnetic field. The fields are storing the energy. So at a point in space where there is field, there is some energy packed into a little volume around that space. Likewise, over here, at a point in space where there is B field, there is some energy being packed into a small volume at that space. So summing those two terms, we get what we might call the total electromagnetic energy density, little u, em for electromagnetic, the sum of the energy density stored in our electric field and the energy density stored in the magnetic field. And we get this nice expression here. So if we consider any tiny volume, dv here, a little tiny volume like this, so with an infinitesimal volume with sides dx, dy, and dz, inside this infinitesimal volume of space, there is energy being stored if in that small volume centered at some point, there's energy being stored at that point if there is electric field at that point and magnetic field at that point. And the magnitude of the electric field squared corresponds to the density of the energy packed into that little volume. And the magnitude of the B field squared also makes a contribution. It corresponds to the density of the energy being packed into this tiny volume.